It's our great pleasure today to welcome Professor McPhedran, who is an emeritus professor in the University of Sydney. He is a Doctor Honoris Causa of Aix-Marseille University, as well as a research associate of this university. He is a fellow of the Optical Society of America, of the Institute of Physics in UK, of the, Australian Academy of Sciences. He has published more than 300 seminal papers in the theory of gratings, photonic crystal, phononic crystal, metamaterials. So Professor McPhedran obviously is extremely famous, and I remember vividly when I was a young PhD student, a research visit of Professor McPhedran at Resonant Institute back in 1998, and I owe my career to us. So I'm very, very pleased to have him today with us. So Professor McPhedran.
Okay, thanks, Seb. This work I'm reporting on has been done with in conjunction with Brian Stout, also of Aix-Marseille, and it's about the same topic that David spoke about just a week ago, I believe. But I'm dealing with one small aspect of the problem, and David's description would have been more general. So it's about resonant states for scattering problems with the added title, Killing Me Softly, and I'll motivate that second part of the title as we go along. So this work was carried out benefiting from an associated laboratory for photonics between France and Australia, and various French government grants, and as well as benefited from discussions with Rémy Colomb, Nicolas Bonneau, Jean-Paul Huguenin, and Philippe Lalande. Here I give some references. The 1992 one was key to all this work, and I'll be speaking about what's in that first of all. It was done in the context of a different application, but the same integrals turned up as are needed to normalize resonant states. The second and third. The third one is a printed version of the talk today, and was published in the Quarterly Journal in 2020. As well, reference 4 is an archive paper. Reference 5 is an old reference due to Carl Bohm, who popularized the singularity expansion method for time-dependent problems, 1971. And I think this work was very influential in the mathematics community, which deals with time-dependent problems in particular. And if anybody wants an excellent book on generalized functions, I use D.S. Jones's book, of which a second edition is still available from Amazon. So the basis of this is a mathematical problem concerned with apparently divergent integrals. These apparently divergent integrals can be dealt with in various ways, numerical or analytic. And the analytic method I will be using there are other ways of getting at the same results. For example, Mellon transforms, deformation of contours into the complex plane, etc., etc. And the results, if the problem is solved properly, agree among all these various methods. The physical context of the mathematical problem is, of course, scattering theory, Me theory is for spheres, of course, in electromagnetism. As well, the results I've been presenting could be applied to cylinder scattering, which is again, a very important problem. The history of this subject is rather convoluted and may be described as perplexing. And to paraphrase Oscar Wilde, who said, "The truth, simple and pure, is rarely simple and never pure," that also applies in this case. Most of the work is based on the 1992 paper. The added thing, which was never was taking limits of integrals over Bessel functions with the Gaussian parameter tending to a constant. So these limits of integrals have to be considered carefully, and that is the new element that was added, which made this work relevant to the scattering problem and to the resonant states. These applications, of course, are for scattering theory, but is more general than just me theory. It could be applied in more complex problems, for example, like elastodynamics. An illustrative example illustrates, in fact, the use of Gaussian killing functions when you're considering an integral, and the next slide will give you the form of that integral. So it's an integral such as those that arise in considering inner products and normalisation factors for resonant states with complex behaviour. These integrands diverge strongly at large distances from the scatterer, as shown in the left panel. You've got a real part in red and an imaginary part in green of the integrand. Of course, but the amplitude of each of those terms increases exponentially. So if you're doing that integral as a numerical exercise, it becomes rather difficult to get a result for which you can have a guaranteed number of figures of accuracy. On the other hand, if you just multiply by a Gaussian, of course, the Gaussian converges to zero as a second power of the radius, so it can eliminate any exponential divergence which goes as the first power of the radius. Even with a small multiplicative factor in the exponent, in this case 0.01, you get a function which peaks and then dies away to zero. The main contribution to the integral may come, in fact, early because there can be cancellation. But there is something that you can deal with analytically and numerically. The situation is much better. The integral, which was illustrated in that previous slide, is actually an integral which involves 4 parameters. It's got a Bessel function of type J and a second Bessel function of type Y. They have different spatial wave numbers, capital K, little k. You've got the order of the Bessel functions, which is common to the 2 Bessel functions. And you've also got your regularization factor of the Gaussian eta. Even with eta equal to 0.01, the divergent integrand is replaced by 1, which can be integrated accurately. And if you do that, then you get the example quoted 0.01648787 minus 0.0138487i for integration with the upper limit 80 or beyond. You can do the analytic value for the integral, as I'll be showing you, with the upper limit set to infinity, and you get which is quite close to the first, but differing in the third figure. If you decrease this regularization parameter, then you have to integrate further, take into account more oscillations. It becomes a lot harder. You improve your answer, but if you go a factor of 5 smaller, the numerical integration in Mathematica fails unless you do some hand-holding on the integral. So the problem is becoming more and more difficult as you take this parameter eta towards 0. That's what you would like to be able to do because this parameter eta is taking the physical integrand and modifying it by this killing function. So you want to be able to get an answer using the killing function and let that killing function tend towards unity to get the appropriate physical answer. The mathematical problem is in terms of two-cylinder function of common order, different wave numbers, as I've said, K and L, and Watson's celebrated book on Bessel functions gives the answer for the indefinite integral in terms of a form in which it looks a bit like a Wronskian, and it's got the K and the L factors on the top and a K squared minus L squared factor on the bottom. These K and L may be real or complex. If you want to use this result in wave scattering treatment for spheres or cylinders, if you're dealing with spheres, mu will be a half integer. If you're dealing with cylinders, a mu will be an integer. If you're dealing with a scattering problem, if you want to evaluate energy inside the sphere or cylinder, you're going to be integrating from 0 up to the cylinder radius, whereas if you want the energy outside the sphere or cylinder, you're going to want the integral from the radius of the sphere or cylinder out to infinity. So you're going to need both of those integrals, and you'd like to have a reliable integration, either analytic or numerical to high accuracy. If you're dealing with purely numerical methods, of course, having exact analytical results to hone your integration algorithm is highly useful. Resonant states are a means of describing spatial and temporal modes of oscillation of open systems. They go back way, a long way into the late part of the 19th century and came into prominence with investigations of decay of nuclei in the early years of quantum mechanics. So they have, due to the longevity of their use and the fact that they occur in scattering problems and time-dependent problems and are used by mathematicians, physicists, and optical engineers, they have a variety of names: quasi-normal modes, transient modes, leaky waves, etc. There are some famous names who've worked on the problem of resonant states and their treatment. Land, Wigner, Piles, and Zeldovich are among the many who've commented on the mathematical difficulty. So The next quotation is from Zeldovich. An exponentially decaying state that describes, for example, the phenomenon of radioactive decay is characterized by a complex value of the energy, the imaginary part of the energy giving the decay probability. The wave function of this state increases exponentially in absolute value at large distances, and therefore the usual methods of normalisation, of perturbation theory, and of expansion in terms of eigenfunctions do not apply to this state. From memory, Zeldovich wrote this statement in the 50s or 60s. Since that time, of course, Fourier methods and the calculus of generalized functions have become better established, and therefore one can, in fact, go further than Zeldovich indicates in terms of normalization and perturbation theory. Perhaps when he says usual, he was well aware of generalized functions as being an unusual method. So where these complex states come from in me theory is the poles of the scattering matrix for the problem of scattering. Writing the problem out in terms of the problem for spheres, you have an equation such as 3 for the poles of the scattering matrix. It's this sort of Wronskian that you get in the scattering problem, where you've got spherical Hankel functions, spherical J functions. You've got these Riccati Bessel functions, which essentially just contain a multiplicative power of the radius for convenience, and the psi is another type of Riccati associated with an H or a J. Here, epsilon and rho denote a dielectric permittivity and refractive index, and Z is the eigenparameter. If I were dealing with magnetically active spheres, this equation would be slightly more complicated. I'd have to put in the magnetic permeability. The poles of the scattering coefficient lie in the lower half plane for materials without gain. Go as e to the IZR, diverge exponentially in amplitude as r goes to infinity, while oscillating ever more rapidly in phase. So you do have a divergence in amplitude in exponential fashion, but you've got this rapid oscillation in phase. So you've got a large amount of cancellation going on and a strong growth in amplitudes, which means as you go further and further out, unless you do something tricky, you have to carry more and more decimals in it in order to get the appropriate degree of cancellation. So the history of this nomenclature, various authors using different nomenclature, the approaches are sometimes numerical, in other cases analytic, but a number of different ways are possible to approach this in the case where an analytic solution is derived. Brian and I got interested in the method I'm now describing because of what I'm just about to describe, which is the work from 1992 associated with Ewald summation, which gave us a set of results which we could use as a starting point. So one has these functions diverging with distances and oscillating rapidly, and they're going to occur in inner products and normalisation integrals. You can use perfectly matched layers, or you can just use Gaussian integration, using killing functions. You can do it either way. In the case of perfectly matched layers, there's a lot of work using them. The results are generally good, but you have to be careful in the case where you're exciting something like a surface wave on the boundary between your perfectly matched layer and the physical region of the problem. However, as Zeldovich in fact pointed out, you can use distribution techniques and a Gaussian kill function. You could use other classes of kill function. Gaussians will be applicable and sufficient in a lot of situations, but you could go to a exponential minus eta r to the fourth if you have the first power. And subsequently, if you can take the limit as eta tends to 0, you'll get a closed form numerical result. Zeldovich was talking about these integrals and perturbation theory approaches in the complex of one-dimensional quantum scattering problems, therefore scalar problems. We'll be talking about the integrals which arise in 3 or 2-dimensional scattering, which are vector problems. We, as I said, are going to consider scattering problems for cylinders and spheres, with the latter referred to as killing me softly. Brian and I, in some of our papers, have used puns based on the pronunciation of the word me. In 1992, with a PhD student and a colleague whom I met on the internet, Tony Scott, we weren't at that time interested in integrating resonant scattering states, but what we were interested in was lattice sums, and doing lattice sums using the classic Ewald summation technique of the 1910s, courses of solid state physics in the period before powerful computers became available. So Ewald summation is a classical and clever technique. It's essentially based on a use of the Poisson summation formula, but it uses both the integral and its Poisson summation form and mixes them in an appropriate way. It's got a regularization factor eta as before, and if you're using it as a numerical technique, you diminish eta until hopefully you find a plateau where your results are stable to 4 or 5 figures. As you decrease eta further, your result will tend to blow up if you're working with computations of finite accuracy. This eta parameter is one of the difficult aspects of application of Ewald summation. But for a fair while, Ewald summation was an essential technique for important problems in solid state physics. So, Gaussian integral, which gives you some idea as to what to expect from the JY integral, but the result for the JJ integral is well known. It actually consists of a Gaussian function multiplied by a Bessel I function. Looking at that result gave us a hint as to how we could deal with the JY integral, which wasn't in any of the standard integral tabulations. By differentiating with respect to various things under the integral sign, we were able to derive a partial differential equation which we could integrate to get equation 6. Now, the beautiful thing about equation 6 is it's got a first term, which is a simple integral readily evaluated, and it's got a second term where instead of having big K and little k and eta and b, 4 parameters under the integral sign, I just go back from that to having a j and a y with the same argument. I've still got e, and I've still got the same orders of the Bessel functions. Of course, I can change the variable now in this and reduce my number of parameters, free parameters, to a single one. The curly h I described there is a function which occurs in plasma wave theory, and it's a finite range integral of a Bessel function, an exponential with arguments u and 1 on u, integrated in the neighborhood of 1. So it's a symmetric integrand with this power law in front of it. So that one is an easy one to evaluate numerically. The previous one I had, as I said, I could simplify that even further using a change of variable, rescaling x to get rid of it under the inside the Bessel function arguments, and I just get then a single parameter on the Gaussian, which could be complex if big K and little k are there, but I've still got the killing factor form. So a result, but one can take that even further. A lot of integration algorithms which are used on computers in fact evaluate integrals using generalized hypergeometric functions, one of which is called the Mayer-G function. And using the Mayer-G function, Tony Scott was able to tell David Dawes and myself what the result of that integral was in closed form. It's an interesting form because it's got this cot factor here multiplying a Bessel function I, and it's got an associated Bessel function which is given here. That was defined and will occur in the book by Luke on integrals of Bessel functions, an associated Bessel function of hypergeometric form, as in equation 10. So you can put those together and you can get the jy integral in this closed form. This closed form is not useful for b integer because of this cot term. So you've got to use a different term using a slightly different argument, and you get instead of one of these associated Bessel functions, you get an I and a Macdonald function K inside the answer for that capital H. So these are the results. We had to spend a bit of time learning how to use these associated Bessel functions because they're not so well known as normal Bessel functions. So one can use these for integer b, and you get all these nice results. You can get an infinite number of results. The results for these just consist of a polynomial of 1 less than the order of the Bessel functions plus a Macdonald function of the same order as the Bessel function multiplied by an exponential factor. And this is all very interesting because I'll remind you that we were going to take the limit as a tends to 0, and therefore a lot of the nasty bits will go to 0. We can see already from these simple results. So with Brian Stout, we took these results looked at for 15 years or longer. So there's a lot of relearning, and we generalize them to other Bessel functions, JJ, JY, JH1, JH2. So to get the other ones, you need to know Y combined with JB and J minus B, and it's sufficient to have JB and J minus B to be able to do a lot of integrals, such as Y minus B is a combination of JB and J minus B, for example, etc. So you can get all a whole range of integrals in closed form, and obviously spherical Hankel functions or cylindrical Hankel functions forms follow from knowing these. So these can be expressed in convenient forms for the important cases of cylindrical scattering, where B is an integer, and Mie scattering, where it's going to be a half integer. So the program of work then was take all these expressions for integrals and then let the parameter eta in the killing factor, killing function, tend towards 0 to get closed form analytic integrals. You're going to obtain in the course of these integrals, you're going to, in some cases, to get delta function results, and you'll recognize that when you get an integrand which can be forced in the form of a Gaussian with an appropriate normalisation factor, which tends as A tends to 0 to the delta function. So if you do that, you get the limit as eta tends to 0 of the JJ integral in terms of a single delta function. It's a single delta function. If I did the whole thing, it would actually be a pair of delta functions, one of k minus k and one of k plus k. But if you know that k plus k can't be 0 in the problem you're interested, you'll get the form 18. General form will involve two delta functions. Okay, so that's JJ, but if you want all the others, then you have to be able to study the first integral is what's called a Swarovski function, if I remember the name correctly. As I said, occurs in quantum plasma dynamics and plasma dynamics in its own right. So one has to consider an integral of the form 90, 19. You use Mathematica to feed that in, and it tells you the result can be expressed in terms of imaginary error functions. It knows how to do the asymptotics as eta tends to 0 of the imaginary error functions. And what you get out of it is nice, because it's the first term from the analytic result of Watson, and then an error term which is of order eta. So that one is going to go to 0, and you're going to be left with this as essentially driving the analytic answer as eta tends to 0. The associated Bessel functions as eta tends to 0 involves some nice details. The series of the this function is a hypergeometric type series, and Prudnikov's tables give you a form which expresses the series in terms of an integral of Gaussian form. We want a slightly more general form, So we can replace the 1 by an alpha by just putting an alpha here in the Prudnikov form. And it's convenient in analytics to, instead of using the Koch and the Shine forms, and those forms hold for all x positive or negative, because they're symmetrized form of those. So these integrals can be derived simply from the previous form, and we take the difference of these two to get the exponential form we want, and that's a Gaussian integral. You've got a Gaussian term inside the exponent of the exponential, and this is another Gaussian. So to do this, you find the maximum of the integrand, which occurs at square root of log x on a. We expand about this, and retaining the Gaussian components, you obtain the approximation to the integrand, exponential term, and then the Gaussian term. You can integrate this in closed form, and you get this exponential, which involves logarithms of x on alpha. So the important thing about all this is that as x goes to minus infinity, this tends to a limit of 0 of that term which we wanted to evaluate for the integral. So we're getting the hypergeometric generalized Bessel function term going to 0 as we expected. So putting all that together, you get the integrals, some of the integrals which you are going to want to apply to resonant states in Mies scattering. The integrals, as I said, have to be done inside and outside the sphere. The integrals inside the sphere can be obtained using Watson's integral. The outside integrals from r to infinity are just given here. There's a Bessel function, there's a delta function, and then a Wronskian type expression of the form that you will remember. And then you obtain for the jy term from r to infinity. You don't have a delta function, you just have this, but with 1j replaced by y in the appropriate places. So what has happened is that these are all the lower type, the lower bound contributions from the Watson integral. They're evaluated capital R, and the only other thing is a possible delta function. So one then has these results. This is the y integral. The y integral also involves a delta function. So these results involve a Wronskian type term coming purely from the inner surface of the integration domain, in other words, the outer surface of the sphere, and a possible delta function. The results involving jj and yy involve the delta function, and the jy does not involve a delta function. If you want to see whether you're going to expect a delta function or not, all you have to do is take the expansion of the integrand for large distances from the scatterer. And if you've got a purely oscillating term with mean 0, you won't get a delta function. If you've got a non-zero constant, then this is going to give you a delta function term, because the Fourier transform of a constant is, of course, a delta function. And all of this stuff can be viewed as like Abel summation, depending on Poisson summation and moving between physical integration space and reciprocal or Fourier space. So the origin of the delta function is readily understood. For me theory, you are dealing with vector representations of electric and magnetic fields built typically from spherical Hankels rather than Bessel J or Y. And one of the nice things about the little h integrals for spherical Hankel functions is that in evaluating their integrals, the delta function terms cancel. So a lot of the integrals just give you zero. The process has led to nothing, but more mathematically, it's led to zero. It's a method of providing a rigorous proof that the contribution from of oscillations about mean zero. The main problem worrying investigators in the past and new people who come into the field is the apparently divergent nature of the fluxes at infinity. This divergence at infinity is only apparent divergence because you've got an oscillation fighting an exponential increase in amplitude. In all physical cases, we deal with frequency ranges which are finite. Whatever our theory is, there is going to be some frequency limit in which it's applicable. And in that frequency range, we've got a bounded frequency range. And therefore, these rapidly oscillating functions have zero contribution to integrals because they oscillate much more rapidly than the finite frequency range function. So using a distribution theory approach, we just get the contribution from infinity can be put into closed form. It's either a delta function or it is zero. The proper physics for Mie scattering indicates zero flux at infinity. As I said at the beginning, the integrals arise, if you're talking about Mie theory or electromagnetic wave scattering by cylinders, they arise in such problems, but they're not limited to electromagnetism. Similar integrals may well arise in problems in elastodynamics and other classes of wave problems. Distribution theory approach was fashionable and well studied in the 60s and 70s. It's perhaps less well known now than it was then, but it's, for me, a beautiful, a neat approach, and it can deal with integrals for which classical integration techniques are unavailing. The results typically involve a delta function arising from a sphere at infinity or zero. As I said, asymptotic argument expansions tell you whether you will have a delta function or not. These results can be used in analytical studies. They give you a method contributions from the outer domain of your scattering region. If you're using a numerical method, of course, you can use these results to provide rigorous results in test cases. And where you do the numerical methods properly, we've seen with the results, for example, of Huguenin that we get very good agreement with his numerics. Of course, if you're dealing with multiple spheres or any other system with finite elements, you can always use E-scribe spheres and multipole methods to prove that the general scatterer of finite spatial extent will give rise to fluxes which will be zero at infinite distance from the set of scatterers. With that, I thank you for your attention and would welcome any comments or questions. Thank you.
Thank you very much, Ross, for this very nice talk. So, as you said, we really welcome any questions, including on the Shakespearean subjects.